Because in the case of overfitting, if you give it any other test case, it will.
Ah, that's the thing I was looking for. We don't really care if it works, if the theta we come up with reproduces the concentrations for our training data. We already know what the answer is for our training data. What we care about is, will theta help us predict? Will theta generalize? Meaning, if we take so we have this x1 through x2 through a general xn. If we start to look at xn plus 1 through xn plus n prime, these are our test cases. Will theta, the theta that we got plus theta naught, is that going to be predictive? Is it going to give us y of n plus 1? We didn't use these in our training. Do you think that's predictive? You already know what's going to be predictive, right? You know, calculating the area under the curve. X. Oh, do you think this is a D? Oh, well, I missed that. So these are test cases, right? So this is the first test case, a second test case, a third test case, all the way through an n prime test case. Each of these are d-dimensional vectors. We're going to dot them with theta and add theta naught to it, and that's going to give us a predicted concentration. What could we do? Now, you might think, well, maybe that won't generalize. Maybe it is, quote, overfitting. However you want to call it. The thing that happens when you see something like this is your intuition suggests that, oh, this is going to work for these 5 cases. And if I give it one case that's never been trained on before, it's going to be terrible. What could we do to try to improve the situation? Yes? So I'm going to take what you said, which I like. It's a great idea. Get more training data. So if we had more training data than we had degrees of freedom, we wouldn't have this problem. Usually. No. Not always. Usually. If you have lots and lots of data, this problem of overfitting is less severe. You don't often have lots. Yep. These are already pretty noisy. Well, so that's another way to try to synthetically generate some extra data. And that can work well too. I mean, there are techniques based on robustness to try to get some robustness in the system. That will help. It can help. I'm going to use a slightly different strategy. We're going to do the following. We're going to take the system of equations that we started with. We have the matrix X. That was the current leg forms as Rose's matrix. The vector row 1s, which has to do with theta naught. We are going to make this matrix bigger than square. We have our n test cases. We're going to add d more equations. And we're going to put in these d equations gamma on the diagonal. But not for the So we're going to put these gamma parameters on the diagonal and generate d additional equations. So remember, we had d plus 1 unknowns and n equations, and n was much insignificant. In this case, n was 5, d plus 1 was 4,501. We will have still theta 1 through theta d and theta naught. And we will only have our 5 test cases, y1 for y5, for example. And the rest we're going to set to 0. So what is this system of equations trying to do with the thetas?
makes the thetas come closer together and like lower the disparity because like you're trying to.
Well, it's going to try to reduce the number. It's going to try to drive them all towards zero. Now, I'm going to come back to it if there's time, but for the moment, exactly what the solution looks like, exactly what this is doing, what it is trying to do is to push down the magnitude of the phase. So it's not going to let you pick very big things. It's going to try to push you to pick smaller things. And probably a lot of small things instead of some big things, for reasons we may get to here. But I want to talk a little bit about what happens. How big do you think gamma has to be? So if I type on the screen, can you actually see what I'm typing? Or is it too small? It's too small, good. And you can't see. So you're going to have to take my word for it. I'm going to stick in 1e minus 10 for gamma. So I'm going to add 1 times 10 to the 10 to the minus 10 to, you can see it there. I can see it there. I'm going to recalculate the theta. Going to change much? So we put all these gammas to be 10 to the minus 10. Some very small numbers. Is that going to change the solution much? It's going to change a lot or a little? How many think it'll change a lot? How many think it won't change very much at all? Okay, so let's see. And that's the new theta. Notice they're not all identical. It's not all the same value. But there are a couple of things to notice about it. They're all much closer together. There's something about the way these systems of equations get solved. The fact that these squares. I'm not going to talk too much about that just at the moment. I want to talk first about how we're going to deal with this. So we got a very different answer for what theta was, this vector of thetas. They're now not, a few of them are non-zero, the rest of them are zero. They're all non-zero. Anybody notice something else about them? Does it look like something you saw before? So if we just happen to have a look at this. Oh, it's gone. Oh, I lost it. Anybody recognize this thing? What does it look like? It looks like a curve waveform? A little. Or start at the beginning, got kind of a little delay, and then goes up, and then it goes down again back to zero. Kind of looks like a curve waveform. Well, that's meaningful too, and we'll talk about that, but not for weeks and weeks and weeks. But the question you should be asking yourself is, okay, so if 10 to the minus 10 help, does 10 to the minus 8, does that help? What do you think will happen as we start to increase gamma? We start to make this number bigger. How well will we fit our training data? Remember, these extra equations are trying to force theta to close to zero. And it's running counter to trying to resolve the training data. That is, we may, by using too big a gamma, we may not fit our training data anymore. So there's a trade-off here. If gamma is too small, we get this phenomenon that's sometimes called overfitting. And what we care about is that we lose generalization. Well, I made that claim, but we're going to need to know how we're going to discover that. If gamma is too large, then we don't fit the training data. what we're trying to do is to figure out what a good value is for this gamma, this thing that's going to try to keep theta from getting too large. It avoids this generalization. Keeps us from losing generalization. We need to find out what that gamma should be. Now, if we throw out one piece of training data using this test data, maybe we got lucky and threw out a piece that's one that's easy to pick. So the strategy that's sometimes called cross-validation is this. You throw out one data, you throw out a subset of data. You calculate the data with a candidate gamma. And then you swap out that subset. And go again. In each one of these cases, you look to see how bad the error is. So you go through it, so you can imagine you're only going to throw out one set of the data. So we had 5. So we're going to train on 4 and throw out the last one. We might throw out every pair. We might throw out 2 data sets and fit we'll train with 3 and then test on 2. And we could, for a given gamma, we could see what the worst case error is in all those different trials. Then we could try a different gamma and do cross-validation again. And a different gamma and do cross-validation again. And we can use this and see which gamma gives us the lowest error on cross-validation. So we can use this, the result of cross-validation, to select gamma. So we're actually going to have you do this on the problem set. But I want to bring up another issue. Well, actually, let me step back for a second and talk a little bit about exactly what's going on in that system of equations. One more. So here's our setting. We have the set of training data.